Part 5 is going to be talking about polarity. So we're going to talk about what polarity is, what it means to have a polar bond, and then a polar compound or a polar molecule. So let's start with what is polarity. Polarity is in a chemical bond depends on the electronegativity difference between two different atoms. So the greater the electronegativity, the more polar the bond. So as we talked about before, right, the electronegativity trend increases up to the right and in a diagonal on the periodic table. And if you have a greater difference in the electronegativity between two atoms, then it's more polar. What are the importance of polarity? Polarity is related to the forces between molecules, or the intermolecular forces. So these are forces between molecules. And if we think about solutions, right, solutions can have two solutes trying to interact together. They can have solvent molecules interacting together, and finally they could have solute-solvent interactions, and this can explain the solubility of a solution. So what is the polar bond, right? The polar bond is an unequal distribution of the electron density, or the pool of electrons. So the pool of electrons, which results in polarity, right? So it increases the difference in the electronegativity between two different atoms. So here we have a nonpolar covalent bond, right? Just two chlorine atoms, right? They have the same electronegativity, so their change in electronegativity is 0, right? So it's a nonpolar covalent bond compared to hydrochloric acid, right? HCl, which has chlorine, which is more polar than hydrogen, so it pulls the electron density away from hydrogen, and thus chlorine becomes partially negative, and the hydrogen becomes partially positive charged, right? So it's the unequal sharing of electrons between atoms. And then finally the ionic bond, which is not a sharing of electrons, right? It's a complete transfer of electrons. So it generates full charges, right? Sodium plus, and then chlorine minus, or chloride, right? Sodium chloride, just like we talked about before. So determining bond polarity. So I'm going to go through basic vector math briefly, because I want you to understand how to take a molecule and determine its polarity. So vectors are these tools used to express both a strength or a magnitude and a direction. So for example, we can think of them as number lines. So let's say we have a vector, I'll call it +5, and it's going to be added to a vector of -5. Well, we have +5 and -5 can cancel, so the vector cancels out. So it's 0, right? 0. Let's do another one, right? So let's say we have a vector pointing up and pointing down. We don't need to know the strength of these four basic bond polarity determinations. All you need to determine is that the direction will cancel. So if something's positive pointing up and something's negative pointing down, then these will cancel, and and the polarities are 0. So again, this is 0. However, what happens when we have, let's say we have a bond pointing at an angle to another bond? So let's say that's something like this, right? So two of the vectors are pointing in opposite directions towards either the negative, right? So this is kind of like, let's think of it as a southwest direction, and this is a southeast direction. Well, however, these vectors can be added together, so let's add them. And what happens is that you draw a parallelogram, and the addition of the vector is in the middle. So it's right here. So that's the only difference that we'll see in different molecules, right? So we could either have one pointing towards the left canceling with one pointing towards the right, or we can have one pointing up and one pointing down canceling out each other, or we can have them forming like this this angle to each other, and in that case the two are going to add together and not cancel out. So if we're thinking about polarity, this would be the polar bond here. The polar bond. Okay, so yeah, let's see a few examples, and then hopefully we can understand this a lot better. So we're going to determine the polarity of different molecules using vectors. So first, you need to be able to draw Lewis structures. If you can't, I would strongly suggest going back to your PowerPoints or a chemistry textbook and determining how to draw these structures very quickly and very efficiently. So I'm going to start with carbon dioxide, because that's the most simplest to see here. So if you recall, right, carbon dioxide looks like this. Okay, and its charges, right, are 0, 0, 0. And we know that oxygen is more electronegative than carbon, so our vectors are going to be pointing towards the negative. So the arrow, right, I don't think I told you this in the last slide, but the arrow points towards the negative. Okay, and then we throw in a tail to be the positive side. So be pointing towards the oxygen atoms. And since we have one pointing to the, towards the right, one pointing towards the left, these cancel out, because it's just like one pointing towards the right, one pointing towards the left, right? If one's pointing toward the right, one pointing toward the left, they cancel out. So hopefully that makes sense. So in fact, carbon dioxide is a non-polar molecule. Non-polar molecule. Okay. Let's look at carbon tetrachloride, right? So again, just going to quickly draw the Lewis structures. Let me get rid of this one. I'm going to quickly draw them because I think it's important for you to be able to do this efficiently, right? So CL4. Okay, and we know that chlorine is more polar than carbon, so we're going to have a vector pointing up, a vector pointing down, and those cancel, and then a vector pointing towards the right, and a vector pointing towards the left. So since all of them cancel, all the vectors cancel, we have the overall polarity of the molecule is nonpolar. So carbon tetrachloride is also a nonpolar molecule, just like carbon dioxide. Hopefully that makes sense. Let's move on. just clear this out. And next we have ammonia. So let's quickly draw this. So then I'm just going to draw it first, like you should draw it, and then I'll add the geometry here. So we have a bond pointing out towards us, so that will be on a wedge, a bond pointing towards the side, and a bond pointing towards the page, which is a dash. Okay, so notice here that you can obviously see that this molecule is polar, but how is this so, right? So again, we have a vector pointing towards nitrogen, a vector pointing towards nitrogen, and a third vector pointing towards nitrogen. And what happens is that these can be treated as the same thing as the previous slide, as being added together. So the best way to do this would be to actually change the direction of the vectors. So I'm actually going to change the directions just to show you again. So if we have one pointing like this, one pointing like this, we can draw a parallelogram and add the vectors together. And if they add the vectors together, then this vector and that vector become this vector, and then this vector and this vector add together and form a huge vector. So thus, ammonia is a polar molecule because the vectors do not cancel. Okay, they do not cancel here. Okay, now I'm going to quickly do this third one, right? The sulfur dichloride. Okay, so let's see how this one looks. So again, just going to quickly draw the Lewis structure, because I just want you to understand what the way of determining the polarity. So again, sulfur is not as polar as chlorine, so the vectors will point here and here. And again, this is the same example as the last one. So since the vectors are pointing this way, right, and they can form well, we can add these vectors together to form a big vector like that. So this molecule is polar. So we can develop a trend here, right? So we know that the bent molecules, those are polar. You can also say that the trigonal pyramidal are polar, but the linear and the tetrahedral are non-polar geometries. Okay, so hopefully that makes sense. We'll talk about one more example in the next video.